right, so in this video, we will be covering Chapter 8. My hope is to get through all of Chapter 8 in one video. We are mostly covering Section 8.3. 8.4, I will introduce you to a little bit of those graphs, but most of them we'll briefly kind of brush through really quickly. Most of them you will not have to worry about being on a quiz or an exam. There's only one of them that we will actually consider as part of the material. So, Chapter 8 introduces us to a new type of coordinate plane. You are used to the XY coordinate system. That's called the rectangular coordinate system or Cartesian coordinates. We are going to be looking at what are called polar coordinates. And this is all in relation to circles and angles around these circles around the coordinate plane. If you go on Google and you look up a polar coordinate graph paper, this is what you'll see. It's a bunch of circles. And we're going to be given, instead of points in terms of X and Y, now we're going to be given a radius and an angle theta. This point here, where what we used to refer to as the X and Y axis intersecting, that's going to be called the pole or the pole. And the positive x-axis is referred to as the polar axis. And then angles will be opening up counterclockwise in standard position, positive angles going this direction, with a radius of r, and that's called the terminal side. So a lot of the same language we saw in the previous chapter, but now just kind of giving it a little bit more detail with the polar coordinate system. So first thing we're going to do is practice plotting points in the polar coordinate system. We can be given the angle in degrees or radians. So in this first example, we have a radius of 2. Remember, these are r theta. So a radius of 2 and an angle of 135. So 135 is in standard position right here, and a radius of 2. So we're counting out 1, 2 circles, out 2 rings essentially here. And this is where you would plot that point. The next angle is 3 pi over 2. And so if we're looking at 3 pi over 2, this is pi over 2, pi, 3 pi over 2 would be right here. But we have a radius of -3. If this is a positive 3, I'd count out 1, 2, 3 in that direction. But I'm going to go -3 from there. So counting out 1, 2, 3 in a negative direction, this point would be right here. Now, what we'll start to notice as we plot these points is that I could also call this point a radius of +3 and an angle of pi over 2. This specific point has infinitely many ways we could represent it. I could add 2 pi and add 2 pi and add 2 pi as many times as I want and come up with new ways to represent that point. And so when we are writing these points, we always want to write them as simply as possible. So the next example, we have -1 and a negative angle. So my angle, negative pi over 4, well, positive pi over 4 would be right here. So that much in a negative direction would be right here. And normally it'd go out +1 in this direction, but I have a -1, so I'm going out -1 in the opposite direction, and that point would be right there. The next one, we have an angle of 7 pi over 4, which is right here, but I have a radius of 0, so I'm not going out any, and that point is just right there. It doesn't matter what the angle is at all. If the radius is 0, it's just right there on the pole. All right, on the next page, we are now going to look at writing polar coordinates. And again, we talked about wanting to write things as simply as possible. And the way we will do that is we will try to represent these with a positive radius and the smallest positive angle possible. But we are also able to look at different ways of representing a single point. So I have the point 5 and pi over 4. And if I want to write this angle where r is positive, so it's still +5, but I want the angle between 2 pi and 4 pi, I can add 2 pi to what I have. So pi over 4 plus 2 pi, which I can rewrite that 2 pi as 8 pi over 4. So 5 and pi over 4 plus 8 pi over 4 is 9 pi over 4. The next one, we want r to be negative, but we want it between 0 and 2 pi. So what we can do then is we can use this bottom formula here where we have r is negative. So now I have a -5 as my r value. And then I can add pi and plus 2 pi n. So I right now have pi over 4. So pi over 4 plus pi, but I want a negative angle. So I'm going to subtract 2 pi. That's like adding 2 pi n where n is -1. So pi minus 2 pi, that would be -5, and then pi over 4. Pi minus 2 pi is minus pi. And pi is the same thing as 4 pi over 4. And pi minus 4 pi would be -3 pi. So -5, -3 pi over 4. Okay. And then that last one, we want a negative angle, but for r to be positive. So we can take what we originally had, r being positive 5, and I had pi over 4, and I can just subtract 2 pi. Well, subtracting 2 pi, that's the same thing as 8 pi over 4. And then I can go ahead and do pi minus 8 pi would be -7 pi. So 5 and -7 pi over 4 would be a positive radius and an angle between -2 pi and 0. Now, one of the other things we can do with polar coordinates is we can convert between rectangular coordinates and polar coordinates. We can convert back and forth. So these are the tools that we have right here. X is equal to r cosine theta, y is equal to r sine theta, x squared plus y squared is equal to r squared, and tangent of theta is equal to the y value over the x value. We're looking at some triangle here, some angle theta. Tangent is opposite over adjacent, so the y value over the x value. And then essentially this is the Pythagorean theorem here to get our r value here. And then x and y, just like with the unit circle, our x value was cosine and our y value was sine, but because we're not working just with the unit circle, it's any circle, it would be r times those values. So using those tools here, we have a point in polar form. We want to convert it to rectangular form. So if I have an r value and an angle theta, and I know x is equal to r cosine theta and y is equal to r sine theta, I can plug in those values. My r value is 2, cosine of 3 pi over 2, and sine of 3 pi over 2. Cosine of 3 pi over 2 is 0, so 2 times 0 is equal to 0. And then 2 and sine of 3 pi over 2 is -1, so that's equal to -2. So my point then would be 0, -2 in rectangular form. I can do this with another angle here. I have 3 and pi, so that's my r and that's my theta. X is equal to r 3 cosine of pi, and then y is equal to r, which is 3 sine of pi. And 3 and cosine of pi is -1, and sine of pi is 0. So this is going to be -3 and 0. So -3, 0 is my rectangular coordinate with that polar coordinate. Now we can go the other direction as well. We can convert from rectangular coordinates to polar coordinates. And when we do that, we want to use the smallest r that's positive, and we want to use the smallest, this should say smallest, positive angle with the terminal side passing through xy, and again, using a positive angle. So what's helpful here is to visualize where this point is. So this is given to us in rectangular form. I shouldn't have printed this with this little 2 here. You can just ignore that. If you have a square root symbol like that, you assume it's a square root. You don't need a 2 right there to tell you what kind of root it is. But we can go ahead and plot this point. So -1, and then square root 3 is about 1.7. So square root of 3 would be up 1 and not quite 2 there. And you always are drawing the coordinate to the origin there to draw your triangle. And so the triangle here, this side is 1 and this side is square root 3. And I can use the Pythagorean theorem, or x squared plus y squared is equal to r squared, to find my r. So x and y, we have the square root of 3 squared plus 1 squared. And that's 3 plus 1 is equal to 4. And so r then would be 2. So with our point in polar form, we already have our r value. I need to find my angle theta. Well, we know that tangent of theta is equal to y over x, so square root of 3 over negative 1, or negative square root 3. And if you want to think about your trig functions, remember that tangent is equal to sine of theta over cosine of theta. And we want to think, well, I know this is something on the unit circle. Is it going to be a 30-degree triangle or a 60-degree triangle? And just from our picture, I can already tell this is the 60-degree angle in quadrant 2. But I can check. I can see, okay, is sine, is it 5 pi over 6? Or is it sine of 2 pi over 3 over cosine of 2 pi over 3? So I want to check these. So sine of 5 pi over 6 is going to be 1/2, and cosine of 5 pi over 6 is negative root 3 over 2. And we want to try and simplify that, but this is equal to root 3 over 3. Negative root 3 over 3. Let's try this one. If I have sine of 2 pi over 3, that is root 3 over 2. And cosine of 2 pi over 3 is 1/2. If I multiply by 2 over 2, my denominator is reduced, and I'm left with just negative root 3, which is exactly what we have. So that means that my angle theta is 2 pi over 3. Now, we tell you in the notes here that it's tangent theta is equal to y over x, but you have more tools than what we gave you. If you don't want to use tangent, if you know that this is root 3 and this is 1, and we already solved for the radius as being 2, you could use any trig function. You could use sine and say, okay, sine of some angle theta is equal to negative root 3 over my radius, which is 2, and think, well, what angle in quadrant 2 does sine equal negative root 3 over 2? And that might be easier for you to think through. And the answer to that would be 2 pi over 3. All right, the next one, we're given the point 0, negative 4. And again, it's really helpful for us to plot that point. So 0, 1, 2, 3, 4, negative 4. And before I even have to think through solving this, this angle here is 3 pi over 2. So I already know my angle is 3 pi over 2. And I know that the radius, I can count it, 1, 2, 3, 4. It's a radius of 4, so that would be my angle in polar form. So we just converted points or coordinates between rectangular and polar form. But the other thing that we can do is we can convert equations. So right now I have x plus y is equal to 5. This is in rectangular form. I can use these tools here for converting from rectangular to polar. So I can replace x with r cosine theta and y with r sine theta. And when you are writing an equation into polar form, you're trying to solve for r. You're trying to get r by itself. Well, I have an r on both of these terms, so I can factor that out, so I only have one r. And then I can divide this over. So r is equal to 5 over cosine theta plus sine theta. Do another example here. I have 3x minus y is equal to 6. So again, I'm going to replace x and y. So 3r cosine theta minus r sine theta equals 6. Again, I can factor my r out. And I can divide over, and r is equal to 6 over 3 cosine theta minus sine theta. The next one is a little bit more involved, and we have x squared plus y plus 1 squared equals 1. So x is being replaced with r cosine theta squared plus r sine theta plus 1 squared equals 1. So r squared cosine squared theta plus r squared sine squared theta. And remember, you can't just square these individual terms. You have to essentially do the box method. If it's helpful, I'll show you how to write that out here. But if I have r sine theta plus 1 and r sine theta plus 1, this is r squared sine squared theta. This would be r sine theta, and 1. So I have r sine theta plus r sine theta would be plus 2r sine theta plus 1 equals 1. At this point, I notice that I have a 1 on each side, so I can subtract 1 from both sides, and then I'm left with this being set equal to 0. And I have r squared on both of these. Well, I'm going to factor out the r squared, and I have cosine squared theta plus sine squared theta plus 2r sine theta equals 0. And because I memorized those identities back in chapter 7, because I was told to, I know that this is equal to 1. So I have r squared plus 2r sine theta equals 0. Because 1 times r squared is just r squared. Well, now I have terms with r's on them. I can pull out an r, and then I'm left with r plus sine, 2 sine, theta equals 0. So r equals 0 and r plus 2 sine theta equals 0. And remember, when r equals 0, when your radius is 0, that's just the pole. That's just that point at the origin. And this one I can solve and get r by itself, and I get r is equal to negative 2 sine theta. And that is my equation in polar form. All right, we can go the other direction as well. And we have converting polar equations to rectangular equations. And the tools we will use are the ones written right here. Other strategies we can do is we can square both sides, we can use an identity, we can take the tangent of both sides, and we can multiply both sides by r. So I have r is equal to 5 right now. It's not a lot to work with. Sometimes it's harder to go from polar to rectangular because you have not a lot to work with here. But I noticed that if I multiply by r on both sides, then I have 5r over here, and I have r squared over here. And r squared, I have something I can replace it with, but 5r, I don't quite have something I can replace it with. I could try an identity, but there's no identities really to use here. Taking the tangent of both sides isn't going to be helpful, but squaring both sides could be helpful. That gives me r squared equals 5 squared. Well, I can replace r squared with x squared plus y squared. And now that is the equation of a circle in rectangular form. There's nothing else I need to simplify. There's just x's and y's. There are no r's and no thetas. The next one says r is equal to 3 cosecant theta. And I'm going to start with using an identity. Cosecant is 1 over sine. So r is equal to 3 over sine theta. And I know that if I have an r times sine theta, I can replace that with y. I'd like to get this onto the other side. So if I multiply both sides by sine theta, then this one goes away, and I just have 3 on this side. And then I have r sine theta on this side, and I can replace that with y. So y is equal to 3 is my equation in rectangular form. The next example, we have r is equal to -6 cosine theta. Now cosine is already in terms of sine and cosine, so it's not like the previous one where I can use the reciprocal. If I square both sides, I end up with a cosine squared, which doesn't really help me, and I have an r squared, which I could replace, but that still doesn't help on this side. What I can do is multiply both sides by r. And now I have r squared on the left-hand side and -6r cosine theta here. And I can replace this with x and this with x squared plus y squared. So now I have x squared plus y squared equals -6x. Well, this is in rectangular form now, but it's not standard form for a circle in rectangular form. So I'm going to add 6 over to the other side, and I have x squared plus 6x. And I'm going to write plus something because I'm going to have to use completing the square. And I added that over, so I have 0, and whatever you add to one side, you have to add to the other side as well. So I need to be able to write this as a single factor squared because that's how you write the equation of a circle in standard form in rectangular form. So my b value here is 6, divided by 2 is 3, squared is 9. So in this box, you have b divided by 2 squared. This is the process of completing the square that you learned back in a Algebra 1 class. This would be like a 8th grade, math class, maybe 9th grade. B divided by 2 squared. And so we're adding 9 to both sides. And what this allows us to do is this is a perfect square now, and I have x, and this value that's going to go in here is my b divided by 2. Oops, 3. There we go. So this number here is b divided by 2. And our b value is this 6 here. Plus y squared is equal to 9. And now x plus 3 squared plus y squared equals 9 is the standard form of the equation of a circle. All right, so we've seen some examples of converting points and converting equations in polar form. Now this is getting into the section 8.4 material where you will be graphing polar equations. Now this looks super intimidating, and if you flip through the next few pages of your notes, you're going to think, this is not possible, I can't do this. This is really crazy looking graphs, and they are. But you are only responsible for knowing a circle, and that is the easiest of all of them. You will only be given very easy circles. So you can see here we have 4 different possibilities. A circle to the right of the x-axis or the y-axis, circle to the left. Those are both with the function cosine and an a value in front of it. And if the a value is positive, it's to the right. If your a value is negative, it's to the left with a radius of that a value. And then if your r value is equal to sine of theta, then it's going to either be above the x-axis or below the x-axis. And again, if that a value is greater than 0, that's a circle with a diameter of a above the x-axis. If a value is less than 0, it's a circle of diameter a below the x-axis. So you don't even need to really think about it. Once we see that a value, we know, and I see the function cosine, it's going to be either to the right or to the left. That 4 is a positive value, so I know it's going to be curved to the right. And I know the diameter of the circle, the distance all the way across it, is going to be 4. So before I even do anything, I know 2, 3, 4, that this is my circle, a circle of diameter 4 to the right of the y-axis. Now, how could we find that by plugging in points? Well, I'll show you. We have theta and r. And the angles theta, I'm just going to use some angles from 0 to pi. So 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and then pi. And if I plug those into 4 cosine theta, 4 cosine of 0 is 1, so this is equal to 4. 4 cosine of pi over 6 is root 3 over 2. So that would be reducing the 4 and the 2 to root 3, which is approximately 3.4. Pi over 3, 4 times, and then cosine of pi over 3 is 1/2, so that would be 2. And 4 and cosine of pi over 2 is 0, so that would be 0. 2 pi over 3, that would be 4 times cosine of 2 pi over 3 is negative root 3 over 2, so negative 2 root 3. And then similarly, negative 2 and negative 4. If I plot all these points, I have 4, 4, so, or 0, 4, so 0, 4. And then pi over 6, I'm going at 3.4. Pi over 3, I'm going out 2. At pi over 2, I'm going out 0, so my radius is 0, so that's that point there. At 2 pi over 3, I'm going negative root 3 over 2, or 2 root 3, sorry. 5 pi over 6, I'm going negative 2, so I'm going the opposite direction. And then at pi, I'm going out 4, but not 4 in the positive direction, 4 in the negative direction. So we get a complete circle there, plotting the points from 0 to pi. And that is the graph of the cosine circle. Again, you can use this pattern and not have to do it with those points. And that is as far as you will have to go with graphing for a quiz or an exam in this class. Beyond that, though, we do have other graphs that I'm going to briefly show you, and you can see them in your notes here. So this first one is called a cardioid, and it's because it's almost the shape of a heart here. So you can see the equations here and what their graphs look like. It's got some step-by-step ways for you to plot it. I've shown you an example here of me plotting some points and drawing that cardioid. The next one is called lemcons. I'm never sure if I'm pronouncing it correctly. It's a French word, lemicon or lemcons. But you can see these shapes here on your notes. They're kind of hard to see on the video here, but if you look at yours, some of them have a little loop there, depending on which trig function you have. Sines have the little loop in there, cosine does not. And then an example of me graphing each of those. Again, you're not responsible for these, but I would like just to be able to show you what these graphs look like. The next one is called a Lemskates. Again, not sure if I'm pronouncing it quite right, but it's basically an infinity sign, either horizontally, vertically, or diagonally, again, depending on whether you're using cosine or sine. And if you're the value in front is 4, then my R value is going to be 2, and that tells us how big of an infinity symbol we are drawing and whether it's horizontal or vertical. The next one is called a rose curve. I think these are kind of the most elegant looking, and that's because it looks kind of like a flower. We've got these different number of petals here, depending on which trig function you're using. Here we have cosine, we have an 8-petal rose curve with an R of 2, and R of 2 with 5 petals with sine. And those are 2 examples of the rose curves that you can graph. And then the last one is called the Archimedes spiral, and this is probably my absolute favorite. It's really interesting. It's a really cool spiral, really cool graph. And the equation is just R equals theta. So if your R is 0, theta is equal to, or if theta is equal to 0, R is 0. If theta is equal to pi over 4, R is equal to 3.14 divided by 4 is 0.7. And that's how I'm getting all these decimals here. And then plotting those points around the polar plane, we get this really cool looking spiral. So depending on how far it tells you to graph from 0 to 2 pi or 0 to 4 pi, so on, will determine the size of your spiral. And that brings us to the end of chapter 8.